Hello, everyone. Good afternoon and happy Friday. Welcome to our lecture. This is lecture number 11 for our inorganic chemistry course. So this is a reminder that on Monday we have our last lecture, and then you have the exam happening next Friday. So we have only one more week of class, of course, to attend. So hopefully, I hope everybody is studying, doing the homeworks, and practicing the concepts for the exam. And please feel free to contact me next week in case you have questions or any issues regarding the homeworks, for example, before the exam. And also if you have any kind of questions about the content, okay? So as I mentioned, so today we have only two more classes, right? In which we will finish our discussion on coordination compounds. So today we will continue the discussion on electronic structure that we started last time. Then we will focus on crystal field and ligand field theories to describe bonding and electronic structure in coordination compounds or complexes having a variety of common geometries, in which we will be focused on octahedral, tetrahedral, square planar, and also tetrahedral distortion of the octahedral, for example. We will also cover the electronic spectra and magnetism. All right, so the last concept that we did last time that we studied was the crystal field theory applied to octahedral complex. So as a reminder, the crystal field theory assumes that the interaction between the metal center and ligands around the metal center is purely electrostatic, and it is an acid-base Lewis interaction in which the electron pair in each ligand or in each ligand donor atom is seen as a point negative charge that interacts with the positive metal atom or ion. And in this case, the crystal field theory to describe bonding in the complexes is based on the repulsive interactions of this negative point charge in each ligand between this point charge and the electrons and the d orbitals of the metal atom. So this repulsive interaction between the negative point charge on the ligands and the electrons in the d orbitals of the metal makes the d orbitals in the metal to split in different levels of energies, and this leads to the several properties that are observed in coordination compounds. So if we are talking about an octahedral complex, we can place the metal in the origin of a Cartesian axis, as for example, if we have X here, Y here, and Z here, for example. So, and then we can approach, as the octahedral complex has 6 ligands around the metal in an octahedral geometry, it is as if we can put each ligand or each negative point charge caused by the ligands in this crystal field description of bonding in octahedral complexes over each one of the Cartesian axes. In this case, we have 6 ligands around the metal atom in this octahedral geometry. So if the crystal field theory is based on the splittings of the d orbitals of the metal, driven by this repulsive interaction between these negative point charges and the electrons in the d orbitals, we can investigate how these negative point charges located on this Cartesian axis or on these locations relative to the metal atom can influence the different orbitals. So this is what we discussed. So if we have the free metal cation, for example, we have that the d orbitals or all the d orbitals are degenerate or they have the same energy. If we have the metal cation, for example, surrounded by a uniform distribution of negative charges, so we have a uniform negative charge around it, the 5d orbitals would still be degenerate, but the energy would be increased relative to the metal cation. So if we go from this uniform distribution of negative charges in the metal cation to a distribution in an octahedral geometry in which we have 6 point charges, negative charges positioned around the metal atom and using, putting the metal in the center of a Cartesian axis containing all these ligands, what we can say is that because the negative charges here, which represent the ligands under this description, because they are positioned directly along X, Y, and Z axis, this means that the repulsive interaction between these negative point charges and the d orbitals of the metal will be stronger, so we will have a stronger repulsive interaction if the orbitals are also positioned directly along X, Y, and Z axis. Therefore, the d orbitals which are positioned or have their electron distribution directly positioned over the X, Y, and Z axis will have the energy increased relative to the body center of energy or the average energy for the scenario of a uniform distribution of negative charges. So the d orbitals with that are positioned directly over the Cartesian axis will be more strongly repelled by these point negative charges that represent the ligands, while increasing their energy relative to the body center, while the orbitals in which have their the orbitals that are positioned in between the Cartesian axis will have their energy lowered relative to the energy body center. And this will generate, therefore, for the octahedral complex, this kind of splitting of the d orbitals, in which here we have energy, and the difference between the energy of these two levels is called crystal field splitting or ligand field splitting. And so we have two sets of d orbitals in this scenario. So the first set, lower in energy, represents the orbitals that are positioned in between the axes, and they are denoted T2G orbitals. This refers the T because they are triply degenerated, so 3 orbitals of the same energy, and the 2G represents symmetry designations that we don't need to go into details here. And then the EG refers to doubly degenerated two orbitals of same energy for the orbitals that are more strongly repelled by these point negative charges because they are positioned directly along the axis, okay? So here we have a representation of the ligands as point charges along the Cartesian axis and the different orbitals and their positions relative to the Cartesian, relative to X, Y, and Z. And then we see that the orbitals positioned along, directly along the axis, will have the energy increased relative to the body center, while the orbitals in between, position in between the axes, will have the energy decreased relative to the body center. So dx, dxy, dyz, and dzx will form the T2G orbitals, the octahedral geometry, while the dx square minus y square and dz square will form the EG orbitals. And then we will have this kind of configuration. So coming from the spherical negative environment to the octahedral environment, we have the three orbitals positioned in between the axes will have their energy decreased relative to the body center of energy by 2/5 of the ligand field splitting parameter, while the two orbitals having their positions along the axis will have the energy increased by 3/5 of the ligand field splitting parameter. And here, this all means octahedral geometry. So the two G orbitals lie at 3/5 of the ligand field splitting parameter above the body center, while the three 2G orbitals are at 2/5 of the ligand field split parameter below the body center. And one of the applications of this model is the explanation of the electronic or the absorption spectra for a complex that has only one electron, such as this complex containing titanium 3+, in which we see this band of absorption in this wavelength that corresponds to the transition of one electron from the T2G level to the EG level. And of course, when we have more than one electron, things get a little bit more complicated because we also need to consider electron-electron repulsion. All right, so one important feature is that this ligand field splitting parameter is caused by the repulsive interaction between the ligands approached as negative point charges over the d orbitals of the metal atom or ion. And interestingly, it has been observed that the ligand field splitting parameter varies systematically with the identity of the ligand, regardless of the metal atom. So, for example, if we consider the series of complexes like this, in which we vary the identity of X, we see that the colors range from purple through pink and yellow, and these different colors, it means different energies of absorption, which means different levels or different magnitudes of this ligand field splitting parameter, because these will change the difference in energy between the T2G and EG orbitals. So this sequence, for example, means that the energy of the lowest energy electronic transition, and therefore the ligand field splitting parameter, increases as the ligands are varied along this series. And this series is followed regardless of the identity of the metal atom. And this means that we can order the ligands in an order that is called the spectrochemical series. In this spectrochemical series, we arrange the ligands in the order of increasing energy of the transitions that occur when they are present in the complex. So for example, this is the example of this spectrochemical series that I just mentioned, that therefore arrange the ligands in the order of increased energy of transitions that occur when they are present in a complex. And this is the order, and it is usually not sensitive to the metal atom, all right? So for example, in this case, for the same metal atom, this means that the optical absorption of the cyano complex will be at a higher energy relative to the corresponding chlorido complex. So the cyano will lead to a higher energy, which means a higher ligand field splitting parameter than the ligand chlorido. So a ligand that gives rise to this high energy transition, such as the cyano or carbon monoxide here, this is referred to a strong field ligand because it generates a strong ligand field splitting. So a strong separation between T2G and EG levels. So these ligands, for example, can be considered high, strong field ligands. Similarly, ligands that give rise to low energy transitions, such as the ones here, they are referred to as weak field ligands. So in addition to the identity of the ligands through the spectrochemical series, so for the same ligand but different metal atoms, we also see a difference. And therefore, we can say that the ligand field strength also depends on the identity of the central metal atom, or ion, in which the order is approximately what is given here by this series. So we can say that it depends both on the ligands and on the identity of the metal atom as well. And then we can see that the ligand field splitting for, in this case, octahedral complexes increases when we increase the oxidation state of the metal atom, comparing here, for example, right? And also increases when we move down a group. So the variation with the oxidation state reflects that the larger the oxidation state, the smaller is the cation and the larger is the charge. And this means shorter metal ligand distances, and then we have electrostatic interaction, and this means stronger interaction energies. If we have stronger interaction energies, we have a stronger repulsion of this negative charge to the d orbitals, and this will lead to a larger ligand field splitting. The increase down a group is because of the larger size of 4d and 5d orbitals relative to 3d orbitals. This means that 4d and 5d orbitals, because they are larger, they can have stronger interactions or overlap better or or interact better with the negative charges represented by the ligands, leading also to a larger ligand field splitting. So this is a representation, therefore, of the variation with respect to the ligands and the metals. Another important concept in the framework of crystal field theory, now that we understood and learned about the splitting of the d orbitals into two sets of energies, is the ligand field stabilization energies. So we have seen that this splitting of the d orbitals in an octahedral complex means that not all the d orbitals will have the same energy, right? So we have that the orbitals will have different energies in an octahedral geometry. Therefore, this means that the ground state configuration of a complex is not immediately obvious, right? So for example, we can then, based on this energy level for the d orbitals, to find out which would be the electron configuration of a complex, right? And then we can use this diagram and apply the building up principle. So we can therefore identify the lowest energy configuration according to the building up or Aufbau principle and the Pauli exclusion principle, in which we have the requirements that first electrons occupy separate orbitals with parallel spins before pairing. So this is the picture that we have for the octahedral field, right? And then let's just focus on this region for now, right? So here we have EG, it's and T2G. So let's first consider like complexes formed by the elements of the 3D series. So if we have an octahedral complex, and then we have configurations from D1 to D3, so the first 3 d electrons in a 3dN complex, they will occupy separate T2G non-bonding orbitals with parallel spins. So the only possible configurations are these for D2 here, so we have 2 electrons, and D3 here, in which we have 3D2 and 3D3 respectively. Here, remember, the energy of the T2G orbital relative to the barycenter, it was minus 0.4 times the ligand field splitting parameter, while the energy here is plus. Yeah, let's just focus on this now. Yeah, is minus 0.4 of the ligand field parameter, and this comes from the fact of this variation here relative to the barycenter. Okay, so that this means that the decrease in energy for the T2G level must be equal to the increase in the energy for the EG levels. So the energy of a T2G orbital relative to the barycenter is minus 0.4 times the ligand field splitting parameter. So if we have 2 electrons here in the T2G orbital in a T2 complexes, the complex is stabilized by 2, because we have 2 electrons, times minus 0.4 ligand fields parameter. Therefore, the complex is stabilized by minus 0.8 times the ligand field splitting parameter, or in the case of a 3D complex, 3 times minus 0.4 of the ligand field splitting parameter. So this gives to the complex an additional stability or an additional stabilization energy relative to simply the electrostatic interactions or the acid-base interaction between the metal atom or ion and the ligand. So this additional stability given by the splitting of the energy of the d orbitals in the octahedral field. So this additional stability relative to the body center is called the ligand field stabilization energy. So this is the ligand field stabilization energy, okay? All right, so we can say that the complexes of D2 and 3D configurations will be stabilized by minus 0.8 versus the ligand field splitting parameter, or minus 1.2 of the ligand field splitting parameter in the octahedral geometry. Okay, so let's now look at another scenario in which we have a 3D4 configuration. So we have 4 electrons to distribute in the 3D orbitals of the metal atom. So in this case, there are 2 scenarios that are possible. So we first, like for the 3 first electrons, they will occupy each one of the T2G orbitals. But then what happens is that for the 4th electron, we have 2 possibilities. In the first possibility, the 4th electron pairs with one of the electrons in one of the T2G orbitals, or the 4th electron will occupy one of the EG orbitals. So whatever happens here, it depends on some factors. For example, in this scenario in which we will have the pairing of one electron in one of the T2G orbitals, this 4th electron will experience a Coulomb repulsion with the electron that is already present in the orbital, and this is called the pairing energy. In the case of the electron occupying one of these EG orbitals, there will be no pairing energy. But in this case, although we avoid the pairing energy, for this electron to occupy this orbital has a larger energy. So this electron has to overcome the ligand field splitting parameter to be able, or to overcome this energy to occupy that orbital. So we have a competition between the ligand field splitting parameter and the pairing energy to determine which configuration will be achieved. So in the first case, where we have the pairing, the ligand field stabilization energy will be minus 1.6 times the ligand field splitting parameter, because we have four electrons times the stabilization of each of the T2G orbitals. So we have the stabilization of minus 1.6 of the ligand field splitting parameter, countered by the pairing energy, represented by P. So the net ligand field splitting energy is minus 1.6 of the ligand field splitting parameter plus P, because this pairing energy increases or reduces the stabilization. In the second case, in which we have this configuration, so 3 electrons in the T2G orbitals and 1 electron in the EG orbital, the ligand field splitting energy will be minus 0.6 of the ligand field splitting parameter, and there are no pairing energies to consider. So another important thing here before we move forward is to pay attention on how these electron configurations here for complexes can be written. So we have T2G and EG orbitals, right? So in this case, for example, in which we have the 4 electrons in the T2G orbitals, we can write like this, as represented here. And in this case, like this, we can represent like T2G 3, Eg1. Okay, so we represent the number of electrons here as the subscript in which one of these different energy levels for the d orbitals. Therefore, which one of the configurations that will be adopted by the complex will depend of which one is larger in magnitude. So for example, if the ligand field splitting parameter has a smaller energy than the pairing energy, this means that a lower energy will be achieved when the upper orbital is occupied to give this configuration. This represents what we call the weak field case, which means weak field, ligand field splitting parameter is small, has a smaller magnitude. So it's the pairing energy is higher, or it costs more energy to pair the electron in the lower orbital than to promote the electron to a higher energy level, to the Eg energy level. On the other scenario, in which we have the strong field limit, is when we have that the ligand field splitting parameter, it has higher magnitude than the pairing energy. So it's more energetically favorable for the electron to pair into the T2G levels instead of being promoted to the EG levels. So the lower energy is occupied by achieving only the lower molecular orbital, the lower orbitals, despite the cost of the pairing energy. So this is the strong field case, large ligand field parameter, or ligand field splitting parameter. So there are these two possible configurations, weak field case and strong field case, for a D4 configuration, but also the same is true for other 3DN complexes, 3D5, 3D6, and 3D7, in which we can have both weak field or strong field case. And as we can see from this image, in the strong field case, the lower orbitals are occupied preferentially. So the lower orbitals are occupied preferentially, while in the weak field case, electrons avoid the pairing energy by occupying the upper orbitals. So when we have the possibility that these two types of configurations that are possible in the weak field and strong field case, so 3D4, 3D5, 3D6, and 3D7, we will also, an important notation that you see in the literature and books is that the species with the smaller number of parallel spins is called a low spin complex. And a species with a greater number of parallel electron spin is called a high spin complex. So if we have a large ligand field splitting parameter, we have a strong field case and a low spin case. If we have a weak ligand field splitting parameter, we have the weak field case in a high spin case. So we can say that octahedral 3D4 complexes are likely to be low spin if the crystal field is strong, but high spin if the crystal field is weak. And the same applies to 3D5, 3D6, and 3D7 complexes. And then here we have for these species, 3D4, 3D5, 3D6, and 3D7, the configurations for the weak field case with the number of unpaired electrons in each case, and the configurations on the strong field case with also the number of unpaired electrons. So strong field, low spin, less unpaired electrons. Weak field, high spin, higher number of unpaired electrons. And then when we are talking about these ligand field stabilization energies, and then we are doing these energy considerations, one important issue that needs to be taken into account is that in order to decide between these weak field or strong field cases, for example, and to calculate the ligand field stabilization energy, when we have a complex, we only need to account for the pairing energy that it's additional to the pairing that already occurs in a spherical field. Okay, so for example, let's take a look at D7 configuration. So in the spherical field, the D7, so we have 5d orbitals, right? So in the spherical field, we have seven electrons, right? No, yeah, 7 electrons like this. So if we have now, so we have 2 electrons that are paired already in the spherical field. So when we go to the octahedral field, and then we do 1, 2, 3, 4, 5, 6, 7. Here in this case, which we have high spin, there is no additional pairing energy because it's the same as in the spherical field. But if we go to the low spin case, we have 1, 2, 3, 4, 5, 6, 7. So in this case, the pairing energy is only P because it's 1 times the pairing energy because we have only one additional pairing energy relative to the spherical case. So this is not 3P. It's only P because it's only one additional pairing energy relative to the spherical case. So this is important to have in mind. So as we saw from the spectrochemical series, so for 3D metal atoms, large ligand field splitting, so strong field case, which means low spin complexes, they commonly occur for ligands that are high in the spectrochemical series, such as the cyano, and high spin complexes will be common for ligands that are low in the series that cause weak ligand fields or weak ligand field splitting parameters, such as fluorido, for example. Okay, so this is for the 3D metals. And then when we go for 4D and 5D series, we saw that these orbitals are larger, so they can overlap better with or can interact more strongly with the ligands. This means that the ligand field splittings for these 4D and 5D complexes are typically higher relative to the 3D series metals. Therefore, if the ligand field are larger, the ligand field splittings are larger, which means that the pairing energies will be much lower as well relative to the ligand field splitting. And in addition, because the orbitals are larger, the pairing energies are also lower because the orbitals are less compact, and then we can make electron-electron repulsions weaker. Therefore, we can say that for metals of the 4D and 5D series, the only possible configurations or the only possible scenarios is that we have strong crystal fields, large ligand field splitting parameters, so strong ligand fields, strong field case, therefore low spin complexes. Okay, but experimentally, how can we check if a complex is like high spin or low spin? One of the important techniques for this is the determination of the magnetic properties of a complex, in which the complex can be, or a compound can be classified or as diamagnetic or paramagnetic. So for instance, diamagnetic compounds are those who are repelled by a magnetic field, while a paramagnetic compound, they are attracted by a magnetic field. And then we can distinguish these two species experimentally by using magnetropy, magnetometry, and also, in addition to that, we can measure the magnitude of the paramagnetism of a complex and report this in terms of the magnetic dipole moment that it possesses, in which higher magnetic dipole moments means a greater magnetism in the sample. So if we have, how does this work? So if we have a free atom or ion, we have that both the orbital and the spin angular momenta will give rise to the magnetic moment and contribute to the paramagnetism. If we have a complex, the orbital angular momentum will be suppressed. And then we will have only contributions from the spin angular momenta. So if we have unpaired electrons in the sample, we will have a net electron spin angular momentum in this complex. And this will give rise to what we call the spin-only paramagnetism, because the orbital angular momentum is suppressed. And this is characteristic of many d-metal complexes. And in theory, we can estimate the spin-only magnetic moment of a complex based on the number of unpaired electrons, which will dictate the total spin quantum number of the complex with this expression. So this is the spin-only magnetic moment of a complex relative to the spin quantum number, in which this is the total spin quantum number, and then this is equals to half of the number of unpaired electrons. Therefore, we can have this expression which correlates the spin-only magnetic moment of a complex with the number of unpaired electrons. So if we now measure the magnetic moment of a complex, the result, therefore, can be usually interpreted on the basis of the number of unpaired electrons that this complex contains. So this measurement can be used to distinguish, to know how many, if the sample has unpaired electrons, and how many unpaired electrons the complex has, and therefore we can distinguish between high spin and low spin complexes. For example, the magnetic measurements on a D6 complex can easily distinguish between a high spin configuration and a low spin configuration, as the low spin will have 0 unpaired electrons and therefore 0 of magnetic moment. So this is like some values for different electron configurations, the number of unpaired electrons, the total spin quantum number, the magnetic dipole moment calculated, and the experimental values, in which we can see a good agreement between calculated and experimental values. In addition to this, another application is that the ligand field stabilization energy also helps to explain some trends in thermochemical correlations, for example. So if we take a look at the hydration enthalpies of several N2 plus ions for the 3D series, we can see that the variation on the hydration enthalpy here that leads to the formation of this octahedral complex, this has this double humped variation. If we only have considerations regarding the size of the metal cations, we would expect only a linear increase, in which with the decrease in the size, an increase in the hydration enthalpy would be expected as a result of the increased interaction between the charges of opposite signs due to the electrostatic interaction. However, and this is what is predicted only considering the size here by the yellow circles. However, in practice, we see this double humped variation, and this variation from this linear profile is due to the ligand field, to the variations in the ligand field stabilization energies, in which at this point we have a zero of ligand field stabilization energy because we have one electron in each one of the orbitals here, and then we match what would be predicted by only the variations in size, for example. All right, so next we will discuss crystal field theory applied to tetrahedral complexes now. But before we start on tetrahedral complexes, let's have a 10-minute break. So let's be back at 1:12. All right, so see you soon. Hello, everybody, welcome back. So now, considering coordination compounds or complexes that have the tetrahedral geometry, we also have to analyze how the d orbitals on the central metal atom will be influenced by the point charges that represent the ligands under a tetrahedral environment. So for the octahedral case, we have that the ligands will point along the Cartesian axis, and then we have the resulting splitting of the orbitals with this pattern, in which orbitals along the axis had their energy raised, and orbitals in between the axis had their energy lowered relative to the energy body center of the spherical case. So in the case of the tetrahedral geometry, we can approach this, or we can approach a tetrahedral complex. In this case, it's very useful to approach it by pointing the ligands or the negative point charges in these positions of a cube, in which the point charges are located in alternated corners of a cube in which the metal atom is present at the center. And this represents the positions in between the main axis of our Cartesian axis system. So in this case, this means that for the tetrahedral complex, an opposite trend is observed, as the ligands are now positioned in between the axes. Therefore, the orbitals position in between the axes will have their energy increased relative to the body center, while the orbitals positioned along the axis will have their energy decreased. So this is the opposite of what we see in the octahedral complex. And moreover, the ligand field splitting parameter for a tetrahedral complex will be smaller relative to an octahedral complex because we have less ligands around the metal atom. We have only 4 ligands instead of 6. This ligand field splitting is because of this electrostatic repulsion. So if we have less ligands, we will have a less electrostatic repulsion, so a smaller ligand field splitting. So this is what happens for tetrahedral complexes, and they are second only in abundance to octahedral complexes for the 3D metals. So 3D metals, the most abundant ones is the octahedral geometry, followed by the tetrahedral geometry. So for a tetrahedral complex, the 4 ligands are placed in between the axes, and the orbitals positioned in between the axes are more strongly repelled, and their energy is raised relative to the body center. Therefore, the tetrahedral crystal field will split the d orbitals into 2 sets of energy, but with an inverted trend relative to the octahedral, in which the 2 e orbitals will be lower in energy than the 3 T2 orbitals. And here we don't have the G configuration anymore to these orbitals because of these symmetry considerations. So here are the position of the different orbitals relative to the negative point charges that represent the ligands for the orbitals position in between the axes and the orbitals position along the axis. And also for the T2 orbitals, the energy is increased by 2/5 of the ligand field splitting parameter for the tetrahedral complex, while the orbitals E have the energy decreased by 3/5 of the ligand field splitting of the tetrahedral complex relative to the body center. So as we have less ligands, the ligand field splitting parameter for the tetrahedral complex is usually lower than for the octahedral complex, is normally approximated by this expression. In addition, the pairing energy is invariably more unfavorable than for the tetrahedral complex. And normally for tetrahedral complex, we only have high spin or weak field cases for the electron configuration. And in this case, for this complex, we also can calculate the ligand field stabilization energies by the same approach that we described for the octahedral complex. And as we always have high spin cases, there is never a need to consider the pairing energy in the ligand field stabilization energy. So here we have the ligand field stabilization energy for the different configurations for the tetrahedral complex. So note here the different configurations using here the orbital notations. Here E comes first because it's lower in energy, for example. And then here we have the number of unpaired electrons and also the ligand field stabilization energy. Sorry, yeah, I felt like I was going to sneeze. And here we have also the values of the ligand field splitting for some representative complexes of tetrahedral geometry. Okay, so this was for the tetrahedral geometry, but when we have 4 ligands around the central metal atom, this means that another possible configuration is the square planar geometry. So even though the tetrahedral arrangement is the least sterically demanding arrangement, so some complex exist as square planar arrangement, which can have a little higher energy. And if we consider like only the electrostatic interactions, we can see that the square planar arrangement of ligands will give a ligand field orbital splitting, which is shown here in this figure, in which the orbital dx squared minus y squared will be above all others. And this is because if we consider a square planar geometry, we have this kind of complex in which here are the ligands or point charges. And this is like the point charges are directly positioned along the axis y and z, for example, y and x and y, for example, and there are no ligands in z. So this means that the orbitals positioned directly along x and y, which is the dx squared minus y squared, will be more strongly repelled, followed by the dxy orbital, which has positions along in between the axes here in the xy plane, while the orbitals positioned along the z direction will have lower energy because they will have lower electrostatic repulsion because there is no electrons or point charges as a result of the ligands in the z direction. So another way to approach this description is to consider an octahedral complex, right? Or to consider an octahedral configuration here for the complex. So here we have the z direction, and then to start stretching the ligands in the z direction. So as we start to stretch the ligands along the z direction, these bonds along z becomes longer, so repulsion along the z direction starts to be lower, while interactions along xy starts to be stronger. So we have that the orbitals positioned along x and y will have their energy raised, while electrons positioned along the z and in between the z axis will have their energy lowered, until we stretch this so large that we completely remove the ligands in z, in which we have a further stabilization of the orbitals containing directions along the z-axis, while orbitals along x and y and directly positioned along x and y have their energy increased. So this gives rise to the crystal field splittings for a square planar complex. So this arrangement becomes energetically favorable when we have 8 d electrons, in which, and also when the crystal field is strong enough to favor this low spin configuration in which all these orbitals are filled in this pattern to favor a large ligand field stabilization energy. So only when the ligand is high in the spectrochemical series, the ligand field stabilization energy is large enough to result in the formation of the square planar complex with 8 electrons. For example, is this complex of nickel. Another important configuration, which is this intermediate case in which we have the octahedral complex and then we distort along the z-axis, so leading to this stretching along the z-axis. This is an important configuration, and this is the tetragonal distortion or the tetragonally distorted complex. So in this case, when we make the ligands along the z-axis farther away, so we have elongation along z and compression along X and Y, and then we arrive at this kind of crystal field splittings. And in this case, this means that if we have complexes of D9 configuration, these complexes of D9 configuration, they can depart from the perfect octahedral geometry, showing some pronounced tetragonal distortion. And this can also occur to high spin D4 and low spin D7 as well, but to a lower extent. And this distortion that occurs for D9 complexes, for example, this tetragonal distortion of the octahedral geometry is an example of the Young-Taylor effect. So the Young-Taylor effect means that if the ground electronic configuration of a non-linear complex is orbitally degenerate and asymmetrically filled, then the complex distorts so that to remove the degeneracy and achieve a lower energy. So this means that if we have a D9 configuration in a perfect octahedral geometry, if there is a distortion such as the elongation along Z, this degeneracy of these two orbitals is broken, and the degeneracy of these three orbitals is also broken, in which orbitals positioned along Z will be stabilized. So this means that for these orbitals, for example, instead of having the 3 electrons occupying the same energy level, we will have this kind of configuration. So we have 1 electron more occupying an energy level, having a lower energy. So this will lead to an increased gain of energy or overall gain in the ligand field stabilization energy, which therefore will drive this distortion, because distortion will enable the complex to have lower ligand field stabilization energy. Okay, so these are the ligand field splittings for octahedral, tetrahedral, square planar, and tetragonal distortion of the octahedral geometry due to the Young-Taylor effect. So another important concept in crystal field theory is the Irving-Williams series, which summarizes the relative stabilities formed by ions of M2+ metals, reflecting a combination of ligand field stabilization energies and also electrostatic effects, in which we have this order, which is relatively insensitive to the choice of ligands, and shows that the increase in stability correlates inversely with the size due to the electrostatic effects also. And beyond manganese, there is a sharp increase in the formation constants, for example, for complex of D6, D7, D8, and D9 with the strong field ligands. And this is because of the additional contribution of the stabilization energies. And for D9, we have also increased due to the influence of the Young-Taylor effect. So this is for the crystal field theory, which assumes interaction to be purely electrostatic between the metal and the ligands. All right, so now we will talk about another theory to describe bond and electronic spectra in coordination compounds, which is the ligand field theory. So now we will move from the crystal field to the ligand field theory. So the crystal field theory, as we saw, provides a simple model that can be used to interpret magnetic, spectroscopic, and thermochemical data. But this theory is an approximation and is not perfect because it treats the ligands as point charges around the metal atom. and does not account for the overlap of ligand and metal atom orbitals. It is an oversimplification and cannot fully explain the variation or the positions of all the ligands in the spectrochemical series, for example. In this case, the ligand field theory provides a more complete description of properties and bonding in coordination compounds, and the ligand field theory represents an application of the molecular orbital theory to coordination compounds. So it refers to the application of molecular orbital theory that concentrates on the d orbitals of the central metal atom. And this, therefore, provides a more complete framework to understand the ligand field splitting parameters. So in the ligand field theory, the strategy here is to describe the molecular orbitals of a d metal complex. So in this case, we can describe the molecular orbitals for a d metal complex by considering the valence orbitals on the metal and on the ligand. So we use the valence orbitals on the metal and the ligand to form symmetry adapt linear combinations of orbitals that can therefore overlap with each other to generate these molecular orbitals. In this case, the relative energies of the molecular orbitals are estimated by using empirical energy and overlap considerations. And let's first consider octahedral complex to show how this works. And initially, let's just take into account bonding or sigma bonding between metal and ligand. So bonding along the main axis of the bond. And then after that, we will consider the effect of the pi bonding and see how pi bonding is essential to understand the ligand field splitting parameter in octahedral complexes. So let's consider an octahedral complex in which each ligand has a single valence orbital directed towards the central atom. So this will be like, will give rise to the sigma bonding. So each ligand has a single valence orbital directed towards the central metal atom. Each of these orbitals has sigma symmetry with respect to the metal ligand axis. Examples of these ligands are ammonia molecule and also the fluorine ion, for example. So if we have an octahedral environment, the orbitals of the central metal atom, they can be divided by symmetry into 4 sets. So we don't need to go into the symmetry considerations for now here, but these orbitals have these symmetries in an octahedral environment, right? We saw here for the d orbitals these symmetries already. So in this case, we have the orbitals with these symmetries and for the metal, and for the ligands, we can generate symmetry adapted linear combinations of the 6 ligands sigma orbitals to match the symmetry of these orbitals of the central atom. So we can have a linear combination between the 6 ligand sigma orbitals having symmetry A1G, TU1, and EG, for example. So here we have 1 orbital, 3 combinations, and then here we have 2 combinations. So we have a total of 6 symmetry adapted linear combinations of the 6 ligand sigma orbitals, and these are all the combinations possible for sigma symmetry to participate in the sigma bonding. And in this case, there is no combinations of ligand sigma orbitals that is possible to give the symmetry of the metal or to match the symmetry of the T2G orbitals. Therefore, these T to G orbitals do not participate in the sigma bonding. So here we have the central metal atom and the linear combination, the central metal atom along in the combining with the scar-tensor axis where the ligands are present, and here the symmetry adapted linear combination of the ligand sigma bonding to give rise to match the symmetry A1G that will combine with this s orbital, here in this case represented here in this picture having also the A1G symmetry. The same for the p orbitals in the metal and the linear combinations having symmetry adapted linear combinations of ligand orbitals of sigma symmetry matching these orbitals. And for the d orbitals, we have here the EG orbitals of the metal and the linear combinations that are possible for the orbitals of the ligands having sigma bonding to interact with these orbitals of the metal atoms. And for the T to G orbitals in the metal, in the octahedral environment, there are no ligand linear combinations that are possible to match these symmetries. Therefore, in the next step, we construct the molecular orbital diagram for this combination of metal orbitals and ligand orbitals. So first, the metal s orbital for s here, and the ligand having A1G symmetry, and the ligand A1G symmetry adapted linear combination, they will overlap with each other to give two A1G molecular orbitals. One bonding, energy is lowered relative to the combination of orbitals making the combination, and one that is anti-bonding. The same for the T1U orbitals of the metal and the ligand. They will generate, so here we have 3 orbitals. So just to make it clear. So this will give rise to 6 molecular orbital in which 3 are ligand and 3 are bonding and 3 are anti-bonding, and they degenerate in energy. So the metal EG orbitals will combine with the symmetry adapted linear combination of EG orbitals in the ligands, leading to a bonding and anti-bonding combination, right? So in this case, we can see that in total there are 6 bonding combinations of orbitals and 6 anti-bonding combinations in total. And here, the triply degenerated T to G orbitals in the metal, they remain unbonding because there are no symmetry adapted linear combination of ligand orbitals having the same symmetry in this case. So this, from here, we can say that the bonding orbitals have mostly ligand character and accommodate the 12 electrons supplied by the ligands. And then the addition, and then so this will be filled by electrons from the ligands, and then the additional electrons will depend on the number that will occupy these levels, will depend on the number of the electrons present in the metal. So the T2G orbital, it remains largely confined in the metal because it's non-bonding, and EG also has metal character. So the N electron supplied by the central atom remains on the central atom mostly. So this arrangement qualitatively is the same as the one given by the crystal field theory. However, the ligand field theory gives a deeper insight into the origins of these ligand field splittings, because also we can consider now the effect of the pi bonding, in which if the ligands in a complex have orbitals of local pi symmetry with respect to the metal ligand axis, as for example, 2p orbitals of an allied ligand, they might form bonding and anti-bonding p orbitals with the metal orbitals, right? So for example, for an octahedral complex, the combinations that can be formed from the ligand p orbitals include the symmetry linear combinations having T2G symmetry. So these linear combinations will have T2G symmetry, so they will be able to overlap with the T2G orbitals of the metal. Therefore, these T2G orbitals of the metal will be no longer purely non-bonding. So let's see what happens. And this will have like different possibilities depending on the relative energies of the ligands and the metal orbitals. So if we have ligands and then they form symmetry adapted linear combinations of T2G orbitals. So if the energy, for example, of the null molecular T2G orbitals lie above or below the energies that they had as non-bonding atomic orbitals in the absence of the overlap or p interactions. So without pi interactions, the T2G orbitals are non-bonding. With p interactions, they can be they will form bonding and anti-bonding energies. So if the energy of these orbitals after the pi interaction, if this will lie below or above the energies of the non-bonding case, this will mean that the ligand field splitting can be decreased or increased relative to the scenario without pi bonding. And when the atomic orbitals overlap effectively, they mix strongly, which means that the bonding are significantly lower in energy and the anti-bonding are significantly higher in energy. If the atomic orbitals have similar energies and symmetries, they will interact strongly, while orbitals of different energies will mix only slightly, even if the overlap is large. So energy and similar energies means better overlap. So we have two types of pi ligands, pi donor and pi receptor ligands. So pi donor ligand is a ligand that, before any bonding is considered, has filled orbitals of pi symmetry along the metal ligand axis, such as this. So the energies of the pi orbitals on the ligands will not be higher than sigma donor orbitals. So the energies will be low, they will be lower in energy than the metal d orbitals. And therefore, when they form molecular orbitals with the metal T2G orbitals, then the bonding combination will be lower than the ligand orbitals, and the anti-bonding combination will be above in energy of the d orbitals of the free metal atom. Moreover, the electrons supplied by the ligand orbitals will occupy the bonding combinations, leaving the electrons originally in the d orbitals of the metal to occupy the anti-bonding T2G orbital. And the net effect of this is that the non-bonding T2G orbitals become anti-bonding, so they are raised in energy relative to the non-bonding scenario, and therefore we will have an effect that the crystal field ligand splitting parameter will be decreased in the presence of pi interactions relative to the case in which we don't have any pi interactions. So considering here the diagram that we just saw and considering only this region, so we have EG and T2G orbitals when we have only sigma interactions. So this is here, this is non-bonding. So for the p donor ligand, we have 3 orbitals or 3 symmetry adapted linear combinations of orbitals here having p symmetry. They are filled with electrons because it's a pi donor. So it lies up below the non-bonding energy than the non-bonding combination of the metal. So they overlap, generating one bonding and one anti-bonding combination. So here, the electrons provided by the ligands occupy the bonding combination, and the electron supplied by the metal occupy the anti-bonding molecular orbital. And the net effect is that the crystal field or the ligand field splitting in the presence of pi interactions is decreased relative to the ligand field splitting in the absence of pi interactions. In the opposite scenario, we can have ligands that are p acceptors, so they have orbitals of pi that can form symmetry adapted linear combinations of pi symmetry that are empty and lie above in energy relative to the non-bonding T2G combination when we have only sigma interactions. So this overlap will generate bonding and anti-bonding combinations in which, because the ligand, the orbitals with p symmetry of the ligand are vacant, this means that the electron in the non-bonding T2G orbital, in the case that we have only sigma interaction happen, you occupy the bonding combination after p interaction of molecular orbitals having this T2G symmetry. This means that the ligand field splitting parameter for the ligands that are p acceptors will lead to an increase in the ligand field splitting parameter relative to the case in which only sigma interactions are present. And this is summarized in this slide. One example of p acceptor ligands is carbon monoxide. So these bond combinations, so the net result is therefore that p acceptor ligands will increase the ligand field splitting parameter. So now we can put the role of the pi bonding into greater perspective, in which the order of ligands in the spectrochemical series is partially that of the strengths in which they can participate in the sigma bonding. For example, these species are high in the spectrochemical series because they are very strong sigma donors. However, when the pi bonding is significant, they show a strong influence on the ligand field splitting parameter. Pi donor ligands decrease the ligand field splitting parameter, and pi acceptor ligands increase the ligand field splitting parameter. And this is the effect responsible for the carbon monoxide, which is a strong pi acceptor, to be high on the spectrochemical series, and OH minus, which is a strong pi donor, being low in the series. So the overall order of the spectrochemical series might be broadly interpreted as being dominated by pi effects, with a few exceptions, in which the general series can be interpreted as follows: pi donor, weak pi donor, no pi effects, and p acceptors. This leads to the increase in the strength of the ligand field splitting parameter. And here are some examples of ligands corresponding to each one of these classes. And here we have a figure summarizing the ligand field, how ligand field theory describes bonding in octahedral complexes here in the absence of pi interactions, so sigma interactions only. So here, when we have a pi donor, here, when we have a pi donor ligand, and here, when we have a pi acceptor ligand. All right, so this is everything that I wanted to discuss today with you. Do you guys have any questions before we wrap up? If not, thank you very much, and I will see you guys next Monday. Bye-bye.